Today's lesson is going to be about isosceles trapezoids, and first off, a trapezoid, if you don't know already, is a four-sided polygon such that exactly one pair of sides is parallel. So you're going to get a parallel set of sides. It's usually pretty obvious which side it is that's parallel. The ones that are converging towards each other. So these are the parallel sides. The parallel sides are called bases. Usually there'll be base 1 and base 2 is how they refer to them. And it would be like B sub 1 in a formula, B sub 2 in a formula, if they were to write a formula. And an isosceles trapezoid, much like an isosceles triangle, has equal sides, but specifically the sides that aren't parallel are equals, or congruent. So this side is congruent to that side. That makes this an isosceles trapezoid. All right, and if I mark all these the same way, this parallel to this, and this congruent to that, and this parallel to this. Now this one here, that's not necessarily isosceles trapezoid, it's any trapezoid for that matter. This is called a mid-segment. And just because, well, I'll just pretend this, let's see, I'm going to say this is congruent to this, and this is congruent to this. We're going to go with that. So, from midpoint of one side to midpoint of the other side, this is not necessarily isosceles. So the isosceles triangle properties, this is any trapezoid. Right. But since these are marked congruent and those are marked congruent, this is a midpoint and this is a midpoint. So, the isosceles trapezoid theorems or properties, first off, when you draw diagonals in an isosceles trapezoid. Okay. Let's just call this diagonal 1. We'll call this one here diagonal 2. The property of those is that they're the same length. So D1 equals D2. So if you get diagonals drawn in an isosceles trapezoid, you should know they're equal. That would allow you to make an equation. The other property has to do with the angles. The angle down here is congruent to the angle down here. The angle up here is congruent to the angle up here. And if I just give them names, let's say this is angle A, and this is also A, and this is B, and this is B, as far as measures are concerned. I know that measure of angle A, or well, let's see. Just fact I'm using the same word. A is the measure, B is the measure. The other property is A plus B has to be 180. And that has to do with the parallel lines here. These are parallel lines. This is a transversal. These are consecutive interior angles. They should be supplementary, right? So these are the same measure. These are the same measure. These add up to 180. These add up to 180. So again, just you see an isosceles trapezoid, you immediately know that all this stuff is true. And then finally, the mid-segment. If this is B sub 1 and this is B sub 2 and the mid-segment's measure, let's say, is M, the mid-segment's measure is the average of the lengths of the bases. So in other words, the mid-segment is equal to B sub 1 plus B sub 2 divided by 2. That's everything you need to know about a trapezoid as far as I know, short of the area formula, which we'll deal with that later. But as far as what we're doing today, finding missing sections in trapezoids or isosceles trapezoids, this is what you need to know. So, example 3. All horizontal beams of the high voltage transmission tower are parallel to the ground. So, this one, this one, this one are all parallel to the ground, which means they're all parallel to each other. So, this parallel to this, which this is the base of the top trapezoid, and from here to here is the base of the bottom trapezoid. But they're both parallel because they're on the same line segment. All right. Measure of angle 1 is 138 degrees. Now angle 1, the way it's drawn, this little cross beam here isn't what we're talking about. Angle 1 is this angle up in here. This is is 138 degrees. And the question A is asking us what's the measure of angle 2, which is way over here. I should put probably 2 marks there. There we go. So, if angle 1 is 138, what's the relationship between angles 1 and 2?
Both of them equal 1. If you add both of them, they equal 180.
They add up to 180, right? Now, it's not like this picture here necessarily, but notice these are both the same, these are both the same. So we have this angle and that angle, but they're the same as each other, right? So these add up to 180, so those add up to 180, right? So in general, we just have an obtuse measure and an acute measure within the same isosceles trapezoid. We know it's isosceles because these are both 10 feet. So we know that angles 1 and 2 add up to 180, so the measure of angle 2 plus 138 equals 180. Okay, and I know that typically geometry students are going to just say 180 minus 138 equals 52, right? That's easy. Why do I have to show my work? This is stupid. All right, the reason you want to show your work is because being able to go from a picture to an algebraic equation is a key skill that you need to develop in this class, because it happens all over the time, all over the place, and they get more and more complicated. So sometimes they're very basic like this, but always write an equation from the picture helps us to develop the skill of being able to do that. So 2 and 138 out to 180, that's the equation I create. Subtract 138 now, and we get measure of angle 2 equals, and it should be 42. I said 52 before, I forgot to borrow. So angle 2 is 42 degrees, and there's our answer for that. Part B says one cross support in the center of the tower measures 4c minus or plus 3, another measures 6c minus 5. What's the length of each cross support? Now, I don't know anything about power lines. I didn't go to school for that. But if they say cross support in the center of the tower, this is the center of the tower. These look like cross supports, right? So again, it's vocabulary I haven't heard before, but I can look at the picture and kind of make a judgment call that they're probably talking about these things. And notice once again we have an isosceles trapezoid happening here because we have the parallel sides, we have the equal sides, and these are the diagonals of those. And the property of this that I just mentioned a moment ago is the diagonals are congruent; they're the same measure. So if one measures 4c plus 3, let's just say that's this one. And the other one's 6c minus 5, let's say it's that one, then of course 4c plus 3 has to equal 6c minus 5. Okay, take the property along with the information to create a good equation. And it does ask for the length of each cross support, so we're going to use this equation to figure out the value of c. I'm going to take the 6c and move it to the left. Moving it across becomes negative. Move the 3 to the right. Moving across becomes negative. 4c minus 6c is negative 2c. Negative 5 minus 3 is negative 8. Divide both sides by negative 2, so c is equal to 4. C's value of 4 gets them to be the same measure. Now it says what's the length of each cross support. The actual lengths are 4c plus 3 and 6c minus 5. So if c is equal to 4, and I do a substitution here, I'm going to get 4 times 4 plus 3, which is 16 plus 3, which is 19. And does it give us any kind of, it's all feet, right? 10 feet, 10 feet, 14 feet, 14 feet, so 19 feet. If you wanted to verify your solution, you could substitute c equals 4 into 6c minus 5 also. They're supposed to be equal to each other, so if I take my c equals 4 and put it here, 6 times 4 minus 5, which is 24 minus 5, which is 19 feet. The fact that that c value gets us the same answer tells me that not only is that the length of each cross support, but absolutely correct. So take your pick on which 19 you want to circle.